There is a planet 64 light-years from Earth that looks, from space, almost exactly like our own world, the same deep shade of blue, the same apparent tranquility when viewed from a distance. You could look at it through a telescope and feel, for a moment, that you were looking at something familiar, something almost like home. And then you would descend into its atmosphere. Winds would hit you first. Not strong winds, not hurricane-force winds, winds moving at 5,400 miles per hour, 7 times the speed of sound. And then, coming sideways through those winds, driven horizontal by velocities that no storm on Earth has ever approached, you would feel the rain, except it would not be rain, it would be glass. Molten silicate particles, superheated until they became liquid, flung sideways through an atmosphere so violent that they would shred through any material human engineering has ever produced in microseconds. You would not survive long enough to measure how hot it was. This is a real planet. Scientists have confirmed its atmosphere. They have measured its winds. They have calculated its rainfall. And the question that researchers who study extreme environments are now asking, seriously, and in peer-reviewed papers, is whether something lives there anyway. Because the history of life on Earth, every time scientists have declared an environment too extreme for biology, biology has eventually proven them wrong. The planet is designated HD 189733b. It was discovered in 2005 and has been studied in detail by some of the most sophisticated instruments in modern astronomy, including the Hubble Space Telescope and the Very Large Telescope in Chile. The cobalt blue color that makes it look so eerily Earth-like from a distance is not water. It is a haze of silicate particles suspended in its upper atmosphere, scattering blue light the same way Earth's atmosphere scatters blue light to produce our blue sky. Below those silicate clouds, the atmosphere reaches temperatures above 1700 degrees Fahrenheit. The winds that carry silicate glass sideways at 5,000 miles per hour circle the planet continuously, driven by the temperature gradient between the side permanently facing the star and the side permanently in darkness. HD 189733b is tidally locked, one face always pointing toward its sun, completing an orbit in just 2 Earth days. The violence of its weather is not a temporary storm. It is the permanent, perpetual state of the atmosphere. Every second of every day, on a world that has existed for billions of years, glass falls sideways through air, moving faster than any bullet ever fired. Could something live there? The honest scientific answer is that we do not know. What we do know is that the category of environment we once called incompatible with life keeps getting revised. Extremophiles, organisms that thrive in conditions that would kill any other known life form, exist in environments on Earth that scientists once described using exactly the same language we now apply to these alien worlds. Too hot, too acidic, too toxic, too pressurized, and every time, biology found a way. Chemolithotrophs live in hydrothermal vents where temperatures exceed 300 degrees Fahrenheit and the chemical environment would dissolve most organic matter. Tardigrades survive exposure to the vacuum of space, temperatures approaching absolute zero, and radiation levels hundreds of times higher than would kill a human. Certain archaea thrive in environments of pure sulfuric acid. The principle that extreme environments preclude life is not a law of nature. It is a pattern derived from a sample size of one planet, from the life we know, during the brief period we have been looking. Now go somewhere colder and weirder. 640 light-years away, in the constellation Pisces, there is a planet called WASP 76b. It is roughly the size of Jupiter. One side of it faces its star permanently. The temperature on that side reaches 4,350 degrees Fahrenheit. Hot enough that the iron in the atmosphere, actual elemental iron, does not remain solid or liquid. It vaporizes. Iron becomes a gas, joining the atmosphere on the day side, getting swept up in the winds that carry atmospheric material from the blazing face of the planet toward the cooler night side. On the night side, the temperature is still over 2,500 degrees Fahrenheit, but compared to the day side, it is cold enough for iron vapor to condense. Iron droplets form in the upper atmosphere on the night side, and then they fall. WASP 76b experiences iron rain, not liquid iron, in droplets, falling from the sky onto a world where the concept of a surface is itself ambiguous because the temperatures and pressures are so extreme that the boundary between atmosphere and whatever lies below it is not a clean line. The espresso instrument on the Very Large Telescope first confirmed this by detecting iron on the terminator, the boundary between day and night, and finding none on the day side. Exactly what you would predict if iron were evaporating on one side and condensing on the other. This is not theoretical. This is measured, confirmed, published physics. No scientist currently proposes that life as we know it exists on WASP 76b, but researchers who study the boundaries of what environments can support life note something important about the iron rain specifically. Iron is not just a hazard. Iron is a nutrient. On Earth, iron is one of the most critical minerals for biological chemistry, essential for oxygen transport in blood, for enzyme function, for the electron transport chains that power cellular metabolism. A world where iron is not scarce but falls from the sky in liquid droplets represents an environment where one of biology's most essential raw materials is provided in extraordinary abundance. The question of whether any chemistry could exploit that Abundance under conditions where every other parameter of the environment would destroy anything we currently recognize as life is a question that has no answer yet. But it is a question that the scientists who study the outer limits of biology are beginning to take seriously. 440 light-years away, there is a planet that requires a completely different imaginative framework. WASP 121b orbits its star in just 19 hours, so close that its star's gravity has stretched it into an egg shape. Its dayside temperature exceeds 5,000 degrees Fahrenheit, hot enough to tear apart molecules that would otherwise remain stable. But what makes WASP 121b specifically strange, and what James Webb Space Telescope observations have been investigating in detail, is its rain. Not iron rain, not glass rain. WASP 121b rains liquid rubies and sapphires. The specific compounds in its atmosphere, aluminum oxide and zirconium oxide, condense on the night side into droplets whose mineralogy corresponds exactly to the materials human beings cut and polish into gemstones. Ruby is aluminum oxide with trace chromium. Sapphire is aluminum oxide in its pure form. The night side of WASP 121b rains both in a continuous cycle driven by the temperature gradient across its permanently locked hemispheres. A world where gemstones form in clouds and fall as rain, across a sky that no biological eye has ever seen, on a surface that the word surface barely describes. Now go to a place that breaks the idea of what a planet's home can be at the most fundamental level. 2,300 light-years from Earth, in the constellation Virgo, there is an object called PSR B1257+12. It is a pulsar, the collapsed remnant of a massive star that exploded as a supernova and left behind an object roughly the size of a city, spinning nearly 700 times per second, and emitting beams of radiation with such precision that astronomers use pulsars as cosmic clocks. And around this pulsar, in orbits that were calculated from tiny variations in the timing of its radiation pulses, there are planets. 3 of them, confirmed. In orbits around a stellar corpse that bathes everything in its vicinity, in radiation levels so extreme that by every conventional model, the surface of anything orbiting there would be sterilized completely and instantly. These planets exist. Their orbits have been measured to extraordinary precision because the pulsar's timing gives us an unmatched tool for detecting the gravitational effects of orbiting bodies. The question of what they are like, of what their surfaces consist of whether anything on them could be considered alive in any sense we would recognize, is completely open. They are the first planets ever discovered outside our solar system, identified in 1992. They orbit something that should have destroyed any possibility of biology in its vicinity, and there are 3 of them, sitting in stable orbits. For reasons the pulsar's existence does not preclude even if our biology-centered intuitions suggest it should. And then there's 55 Cancri, 40 light-years from Earth, twice the size of our planet, 8 times its mass, orbiting its star in 18 hours at a distance of 1.5 million miles, where the temperature on its surface reaches 4,400 degrees Fahrenheit. Scientists analyzing its composition from the ratio of carbon to oxygen in its host star concluded that this planet may be composed substantially of carbon, compressed by the pressures of its own gravity into diamond, not in small amounts, potentially in quantities that make the entire concept of resource scarcity meaningless. A planet that may be, in its interior, a world of compressed crystalline carbon. Its surface, if surface is the right word for something at 4,000 degrees, where rock itself becomes a gas, would not be walkable in any sense that a biological creature could use that term. But the deeper interior, under sufficient pressure, and at temperatures that begin to decrease with depth, might present chemistry that operates at scales and under conditions that our frameworks for what chemistry can support are inadequate to rule out. What all of these planets share is not habitability in any sense that a human biologist would currently endorse. What they share is the property of being genuinely extreme in ways that we once considered the end point of a conversation about life, but that the history of biology on Earth suggests might be the beginning of a different conversation. Every time a new category of extreme environment was identified on Earth, it was followed, with varying delays, by the discovery that something had already been living there, quietly, for millions of years, exploiting chemistry that we had not yet thought to look for. The deep ocean floor, the ice of Antarctica, the cores of nuclear reactors, solid rock miles underground, the acidic lakes of Yellowstone. Each of these places was described, at some point, as incompatible with life. Each of them turned out to contain life. Not the life we expected. Life that had found a way to exploit precisely the conditions we had classified as barriers. The universe is not short of extreme environments. It may, in fact, be mostly extreme environments, with the mild, temperate, water-bearing habitable zones that we consider most promising for life, representing a small minority of the total available real estate. If biology is as creative and as opportunistic under constraint as its history on Earth suggests it is, then the most dangerous planets in the known universe are not necessarily the most empty ones. They may be the most interesting ones. The places where whatever life has managed to survive has been pushed by its environment to find solutions, so far outside the range of anything we would recognize that our instruments, calibrated for the life we know, would not register it at all, not because nothing is there, because everything there evolved to exploit conditions that we have spent most of our scientific history describing as fatal.